Okay, so in the last class, we were discussing about temporal overlap between the windows and how that does not improve the time resolution. This is very similar to the fact that if you oversample a signal more than the Nyquist rate, you're not doing anything you know uh, better than what you were doing before. Um, you will get more estimates and a denser looking spectrogram with more number of values between any 2 points, but those are highly correlated with each other. So it's not that you are actually improving the resolution, you are just smoothing the spectrogram in some ways. So so that was one point. There was another point that how do you estimate the phase? And the idea there was that there are actually two basis functions inside each tile. One is a sine and a cosine, and together they are used to estimate the phase. And there was an interesting, important point that was raised towards the end of the class, end of the last class. So I had mentioned that you can either use a complex exponential or use sine and cosine, or a cosine with a shifted phase, right? Um, so this cosine with a shifted phase, it's a real basis function. So it's true for all real signals. If it's a complex signal, then you need the sine and cosine with that j multiplied with the sine to represent. If it's a real signal, then you could have a basis function which is just cosine with a shifted phase. And at this point will be made clearer when we use a technique called matching pursuit, which we will cover in the next few classes. So so yeah, that's that. Every signal that we see, like this blue trace here, can be thought of as a linear combination of all these basis functions that you, this black one, the green one, the red one, and so on. Um, so you're essentially now representing the signal in two dimensions: time along the x-axis, frequency along the y-axis. And the color that you see here is just the inner product of the basis function with with the signal. Okay, and if the signal actually oscillates in the same way as the basis function, so here, for example, the two seem quite aligned, then you will have a larger value of the inner product. And even if you are shifted out of phase, or like 90 degrees apart, because there are two of them, they will be able to capture the modulation irrespective of the phase shift. And what you see here is the is the sum of the squares and then the root of the inner product with both these functions, sine and cosine. Okay, so are there any questions on this point, or can I move forward? So I'm assuming you guys can hear me, right? One of you say yes.
Yes.
Yeah. Okay. Okay. Thank you. So so we have actually just talked about this point, temporal overlap between the windows. Whether the shape of the window determines the time frequency resolution is something that I'm going to cover later today. But before that, let me talk about something that is called zero padding, and just briefly discuss that. So just use my uh, yeah, pen here, and just talk about one thing that is often done and just discuss that approach with you guys a little bit. So suppose you've got a signal. Here's your signal, and so it's so suppose it has 1,000 points, 1,000 samples. Okay. So when you compute its Fourier transform, so now this is frequency. So suppose this is how it looks like. Symmetric about this. The frequency resolution. So this will also will have 1,000 points, and this is going to be your Fs, the sampling frequency. So suppose your Fs is 1,000, so hertz. So 1,000 point means a duration of 1 second. So you will have frequency resolution of 1 hertz, right? So 1,000 points sampling 1,000 hertz. So 1 hertz is your resolution. So here's one little thing that I can do. Suppose I just add a bunch of zeros after the signal. Suppose I add, let's say, 1,000 other zeros. They're all zeros. So this is what is called zero padding. Now when I compute the Fourier transform of this signal, what is the frequency resolution now?
Point 0.5.
0.5, right?
Yeah.
Because now the duration very good. So it's a signal of length 2 seconds. So the frequency resolution is now twice. So you'll have points at uh, 0.5 hertz. So have you really improved the frequency resolution by adding zeros? On the face of it, yes, you are getting now more points tiling your frequency axis, right? So it's 0 to Fs, but now there are 2,000 points. Fs is 1,000. Now there are 2,000 points. So the resolution is 0.5 hertz. So have we really improved the frequency resolution by just adding zeros, appending zeros? Now in the face of it, you would say, yes, now you have got more points, but really that can't be true, right? Because I could have added a million zeros and I could have had like extremely high density of points between 0 and 1,000 hertz. So that can't be right. Just by adding zeros, I shouldn't be able to improve my frequency resolution. So what has happened? What is the relationship between the spectrum of this original signal and this new signal that has the original signal with a bunch of zeros padded at the end? So the idea here is, so by the way, this technique is often used in signal processing. You will find that often a signal is padded with zeros. Now, there are two reasons why it is done. One is a rather genuine reason, which is that um, back in the days when the Fourier transform, this FFT algorithm was used, it was much faster when the number of samples was a power of 2. So there's a particular algorithm that was used, which would basically be very easy to implement if n was 1024 or 2048, 512. Even now we see that many algorithms actually just try to get some signal length n, which is a power of 2. Okay, it just makes FFT computation very fast in the classical setting. Nowadays, there are variants of this FFT which is very fast, even if this doesn't hold true. Um, we won't get into those details, but this requirement of having n as a power of 2 was there, like 2 decades ago or 3 decades ago, when the algorithms really needed this. Nowadays, it's not such a big deal. So you could just work with 1,000 points also, and it's fine. But often you get an option to add, let's say, 24 zeros, so that the final signal is 1024 points. Okay, so you often zero pad to make the overall signal a power of 2. Even in the Chronux package that I talked about in the multi-taper, there's a padding option. If you set it to 0, it will just make the length equal to the nearest power of 2. So the question is, and then that's the first reason why you would zero pad. That's a genuine reason. And the other reason is that there's apparent increase in frequency resolution because you're getting more data points, as you have seen here. Frequency resolution increases. But actually, there's no true increase in frequency resolution. Now, if you think about this, I'm going to use the Jamboard today. What is really happening is that you have multiplied your signal. So this is your original signal. Okay. And the spectrum that you want, the Fourier transform that you want theoretically, is the one that you would get if you had the luxury of looking at the signal for an infinitely long duration, right? So that is the spectrum that you want, and everything else is a bit of a compromise. So if this is your true spectrum, it's a bit of a compromise because you can only look at the signal for a finite duration. Now, if you are zero padding, essentially what you are doing is you're thinking of this as if you had an original signal that you could look at for 2 seconds. Suppose these are 1,000 points, but you have multiplied it with a function which is 1 for 1,000 points, and then it's 0 elsewhere. Okay, so even if you get samples at every 0.5 hertz now, 1, this 1, 2, sorry, I'm not drawing it very well, um, because apparently the duration is 2 seconds. This is the case where this is 1 second and I have padded 1 second worth of zeros. The spectrum is not the one that you would have got if you were able to look at the signal for 2 seconds. That is the true spectrum for which has 0.5 hertz resolution. That is the true spectrum, assuming you had the luxury of looking at the signal for 2 seconds. But you don't have that luxury. You only look at the signal for 1 second and then you pad 1 second worth of zeros. So it's equivalent of having a 2 second long signal multiplied by this rect function, which is 1 for uh, first 1,000 points and then 0. So there is again a distortion of the true spectrum because it's getting convolved by the Fourier transform of this rect function. So if you get more and more zeros, so if you had like 3 seconds worth of zeros, it's basically now more and more distortion of the true spectrum, which is the spectrum of this signal, with this function, which is now 1 over only 1 second and then 0 over a larger period. So this function has a Fourier transform and you are convolving the true spectrum with that to get the final spectrum that you see. So even if you have more points, doesn't mean that you are improving the frequency resolution. The only way to improve the frequency resolution is to actually have a long window or to be able to compute the Fourier transform of this long signal. If you only look at a part of the signal, you cannot actually improve the frequency resolution. These are all hacks. Zero padding is a hack. You will get more frequency points, but they will all be related to each other, much in the same way that taking baby steps in time domain, this temporal resolution that I had talked about in the previous class, smooths the spectrum. It doesn't improve the time resolution. Okay, so we often see even now that people just append a bunch of zeros and say, hey, now my frequency resolution has improved. That is just not right. And trivially, it cannot be the case because just by adding zeros, how can improve the frequency resolution? It's the same logic that we have seen here applied now in the time frequency. Taking baby steps, I am not improving the time resolution, and by zero padding, I am not improving the frequency resolution. I'm just getting more data, but they are just obtained by convolving the original one and adding intermediate points. They are related to each other in frequency. So as shown here. Now, instead of having samples at 1 hertz resolution, this is what I would have got for the original signal. If I pad zeros, I'll get more data points. I'll get intermediate data points, but they are not going to be independent of these. Essentially some sort of a weird convolution with this. So you're going to get more data points, but it's not improving your frequency resolution. Does that make sense? Because the final spectrum that you are seeing here is just the convolution of the true spectrum that you would have got if you had 2 seconds, but it's getting convolved with the Fourier transform of this rect function, which is a sinc function. So it's basically just smoothing the frequency axis. Okay, that's all I was going to talk about zero padding. Uh, are there any questions? Does this make sense?
Yes, sir.
Okay. Um, so the frequency resolution, time frequency resolution is actually not dependent on the temporal overlap between the windows, nor it is dependent on the zero padding. It does depend on the shape of the window, which I will cover towards the later part of today's class. Um, so I will now, before I get to that, just put multi-taper method and wavelet transform, which I will cover very briefly in this course, in the same time frequency tiling, filter bank interpretation. Okay, so here's the time frequency spectrum um, obtained using short time Fourier transform when computed using two different types of windows. Okay, so this is the tiling diagram when I use a short window, and this is the tiling diagram when I use a long window. I'm just showing two different frequencies, a low frequency basis function and a high frequency basis function. Here I'm using a Gaussian window. These are the tiling diagrams, and these are the spectra that you would get if you use short time Fourier transform over the signal that you have. And as shown before, you get a good time resolution, so you can capture the transient very well. You get good frequency resolution, so you can get the oscillation very well in the um, um, uh, in the longer window case. When you average across multiple trials, you have got 76 trials, you would get a spectrum that looks like this, average spectrum for a short window and a long window here. Usually what we do is, instead of looking at the absolute power, we look at the change in power from baseline. Baseline is before stimulus onset. So you compute the spectrum before onset and then just look at how much it changed. And then this change in power is shown here. You can very easily, nicely see the transient response, but not the oscillatory response with a short window and vice versa. Okay, so this is a short time Fourier transform with a short window shown in A and a long window shown in B. Okay, so now tell me something. This is a hard question. So again, I would like you guys to just guess and think about the answer. So the question is, how is multi-taper method fitting in this framework? Okay, please guess if you don't, no easy answers in this one. So when I say, so you guys remember the multi-taper method, I hope. Let me just show this again. This is windowing, multi-taper method. The idea is that you will have a bunch of different windows or tapers, and they all have a spectrum that looks like this. So this is the first taper, second, third, and fourth. And then you essentially take an average response of all of these spectra to get your multi-taper spectrum, right? This is the padding option. -1 means don't pad. Um, so in this framework, how is multi-taper method fitting in?
So in the when we learn windowing, basically we have only one window, but in multi-tapers we have multiple windows.
That's right.
And here, if we are thinking about it like a tiling diagram, if we take like multiple kind of diagrams and then average out, then probably we can have both capturing of transient as well as the frequency wavelet. We are taking the average of all the tiling diagrams.
No, we are not. So think about this. This is again not straightforward. So suppose I do multi-taper method and my window length is the same as this one. Okay, the long one here.
Mhm.
Okay, but I'm going to say I'm going to use 3 tapers. How is the tiling diagram changing? Or suppose I say my TW product, if you have here, let's say this is set to 3. So now the window length is the same. These are the different tapers there. They all have the same length.
Mhm.
So how is this tiling diagram changing?
The use of this system.
Someone else wants to guess?
Using the same time window, but having multiple basis function with a different frequency.
No, but they all, the basis functions, are they sitting at different frequencies or are they sitting at the same frequency?
Uh,
The frequency is determined by how it's oscillating.
uh,
That oscillation is just the window, whatever you are multiplying, multiplied by e to the power j omega t. That omega is fixed. So when I use multi-taper method, the different windows or the different basis functions are for the same frequency. That's how you get multiple estimates at the same frequency, right? When you get here, so when I use this taper or that taper or that taper, they all have a low pass characteristic. When I do e to the power j omega t while taking the Fourier transform, this gets shifted to that center frequency. So all of these are filtering essentially the same frequency when you're taking the inner product. That is why you're getting multiple estimates at each frequency. Right? So when I use multi-taper method, it's not that my different tapers are actually looking at different frequencies of the signal. I'm using the multi-taper method here when I say I'm going to take the windowed Fourier transform with this window. So what am I doing? Let's look at the formula just so that this point is clear to everyone. Um, yeah, so let's look at this formula. Forget the tau. Okay, so this is short time Fourier transform. Think of it as a Fourier transform, windowed Fourier transform. You've got a signal, you've got a window, ht, e to the power minus j omega t dt. And you're thinking about this as an inner product with the signal and a basis function, which is the window and the complex exponential. Okay, and this complex exponential is what is going to shift the filter to a different frequency. It's the window here. This complex exponential puts it at different frequencies. So when I look at a filter bank interpretation of just the windowed Fourier transform, then essentially what I have in this case is the window. So this is the Fourier transform interpretation of just the Fourier. This is the filter bank interpretation of just the Fourier transform. So what you are saying is that my window function ht has some Fourier transform, and it is usually a low pass filter. So for a Gaussian, for example, if this is Gaussian, this is going to be the Fourier transform. This is the Fourier transform of just ht. And when I do this, multiply it with this, because this is in the frequency domain is a delta function. sitting at omega naught. When I take a product, the Fourier transform of this is just now the same thing sitting at omega naught, whichever is your omega here. So the Fourier transform, it can also be thought of as a filter bank interpretation, where you are filtering it with a bank of filters that are uniformly spaced. And every inner product here gives you one value, and that is the Fourier transform. So even the Fourier transform has a trivial filter bank interpretation. When I do multi-taper method, now I have got a bunch of filters. They are all low pass like this. So when I do multi-taper analysis, so again I am using multiplying with a window like this. So this is your HT now, H1T rather. When I do e to the power j omega t, it gets the filter gets shifted to whatever your omega is. So this thing is just going to shift to that frequency. So will this one, so will this one, so will that one. And then this is now the Fourier transform of the signal multiplied with the first taper and then taken Fourier transform off. And then you do it for each of these tapers and average them. Okay, so this filter bank interpretation also holds for windowed Fourier transform. In every case, you're actually just using a particular filter to compute how much of the signal resembles this particular filter. Even if you didn't have this and you were just doing the Fourier transform, essentially your filter bank, if you're just doing Fourier transform, which means HT is just 1 or is not there at all, it's still your signal multiplied by a sinusoid like this and a sinusoid which is faster and a yet faster sinusoid, right? So this is omega 0, omega 1, omega 2. And all you are doing is asking how well is the signal resembling this. So you're taking the inner product of this with that. And whatever is the value, you're putting that. So you're getting a value here, you're getting a value there, you're getting a value there. And that's your value along this axis as a function of frequency. Okay, it's flipped here. The lower frequencies are below, the higher ones are above. But the idea is that the same thing. So always you are looking at a particular filter. That's the filter bank interpretation of Fourier transform. And when you have a window, it just sort of localizes it better in time as well as frequency domains. Okay. So what are we doing when we have multi-taper method? You have got several tapers. You've got several windows which you are going to be multiplying with the same function. So you will actually have several values at each of these tiles. That is the multi-taper method, right? So you're computing the spectrogram for each of these tapers, but you have several such spectrograms. So there are several basis functions sitting inside each tile. But now the question is the size of the tile the same or not? And the answer is that it's not, because this tile has TW equal to 1. And for my multi-taper, it is some other number. It is some number that you choose. So let's say when I say TW is equal to 3, what I have done is that I'm using a width which is 3 times the minimum possible width. Okay, so the filter bank interpretation of multi-taper is actually very elegant. It's that I am making my tile bigger because this allows me to put more basis functions inside the tile. Okay, so this is with TW. So if I have TW time frequency bandwidth of 3, I will be able to put 5 tiles inside it. They will, which will all have energy more or less concentrated within the tile. Okay, so here TW is 2, so it's twice as big as the previous one. But now I can have 3 basis functions which are reasonably well concentrated, whose energy is reasonably well concentrated with inside the tile. So multi-taper method actually is trading off resolution by increasing the size of the tile, but allowing improving the reliability, but by allowing me to put more basis functions inside the tile. Does that make sense? It's a very cool interpretation from a point of view of this filter bank. It's like I've got bigger boxes, but there are more items inside the box, the item being the basis function. And I'm showing you the 2 basis functions now here. These are the first multi-taper, first taper and the second taper. They will both correspond to a tile somewhere here. These would both correspond to a tile somewhere here. It's a lower frequency. These values correspond to now the average of the inner product with both the first and the second basis function. So it's a more reliable estimate than what you are getting here. Okay. So you are trading off your resolution and the reliability. You could have made it a much larger tile and you would have a ton of basis functions, all of which are more or less concentrated in energy within the tile. Remember that as your taper number increases, that you see here, more and more energy leaks out. Here, the spectral concentration is wonderful. Most of the energy is within whatever you have specified your W to be. And as your taper number increases, this, there's more and more leakage. So you could have taken even more than 5 tapers if for TW equal to 3. But those ones would have such a poor spectral concentration that they are just smearing the energy all over the place. It's not concentrated inside the tile of your choice. So it's of no use. It's just smearing everything. But the first few tiles, first 2 TW minus 1 tiles are nicely concentrated in frequency. So when you multiply it with the basis functions, they are actually nicely concentrated in energy where you want them to be. So the inner product that you get is actually um, a reflection of how the signal energy is at that time and that frequency. Okay, so this is the multi-taper method in the time frequency spectrum. You are using fatter tiles. You are letting go of your best possible frequency resolution. But in the process, you are also gaining better reliability. Here, the spectrum looks crappier than what you had here because this is the average of 76. If you only had 5 or 10 trials, you would actually be able to see gamma rhythm here, which would barely be visible in this if you only had 5 trials or 2, 3 trials. So your gain in the reliability is substantial if you only have a few trials. If you have a ton of trials, then multi-taper is not of much use. Okay, so this is the filter bank interpretation of multi-taper method. I hope this makes sense. Are there any questions? If there are any questions, please go ahead and ask. Okay, so I'll take this as a yes, um, and move forward and talk about very briefly about a method called wavelets. Now, wavelet transform is a course in itself. You could in fact take such a course in IISc also, I suppose. It's a huge topic in itself, but there's no way we can deal with this complex topic in such a short in such a short duration. So I'll just give you the gist of wavelets within this filter bank interpretation. And the idea here is as follows, that okay, I'm going to tile my time frequency space with a bunch of tiles, and my time frequency uncertainty principle tells me that the tile cannot be simultaneously localized in time as well as frequency. If it's poorly localized in time, as shown here, it will have good frequency resolution. But if you try to improve the time resolution by squishing it, then this will increase. So that's the limitation that I cannot overcome. But the short time Fourier transform as well as multi-taper method here is using another has another restriction, which is that all the tiles have the same shape. They are tiling the time and frequency dimensions in a uniform way. When I use a window and translate it, it's the same it's the same way of looking at the signal. It's the same multiplication with a window here. And in the frequency domain, it's again essentially becoming the same thing. This is the filter, which is equi-spaced. The filter which is remains identical as I move along the frequency dimension. And that doesn't really have to be the case. What if I want good time resolution at higher frequencies, because it's a sharp transient. So the signal is actually this sharp transient and then an oscillation like this, right? So suppose I say I need good time resolution at higher frequencies. So I need a tile like this so that I can capture this, and I would need good frequency resolution at lower frequencies. So I would like a tile like that. Can I now have a more sophisticated tiling diagram which will allow me to have tiles of different shapes tiling your time frequency space? Okay, and wavelet transform is one transform which allows me to do that. So I will very briefly explain the math here. It's just in one slide. So the idea here is that this is like taking the Fourier transform as before. So I'm taking the integral of my function, whatever this is, and this is my signal, with something which is like my basis function, a windowed sinusoid. But this is a function which I can scale. Okay. Now think about what happens to a function when I squish it or stretch it. So suppose I come come up with a function which looks like this. This is what I will call a wavelet. What is a wavelet? It is just a function in time which has some nice properties. I won't really talk about those properties in a lot of detail. There are some conditions called criteria called admissibility criteria, which a wavelet needs to satisfy in order to qualify as a wavelet. So for example, its mean has to be 0. It has to have finite energy. Those are conditions that needs to be satisfied. But once a function satisfies it, it is a valid wavelet function. So think of this as a basis function, much like this one. Okay, so this is a basis function, so is this. And this is going to be occupying some space here like this. Okay, so it has some duration. So it is stretched in time with, let's say, this 100 millisecond duration, and it has some frequency. Now, what happens if I squish this function by a factor of 2? This is from short time Fourier transform in which the this envelope never changes. It's the same envelope applied to a low frequency as well as high frequency. Here, this is an oscillating function which I have squished by a factor of 2. What do you think squishing a function in time domain does to its representation in frequency domain? This is a property that we had seen a long time ago. I guess you guys have forgotten it. Let me just go back when we were discussing Fourier transform
It
and looking at the properties. So, linearity, time shifting, I guess it's not here. But I think we did at some point what happens to the frequency representation when a signal is just squished in time. So instead of t, if I do t by 2, what happens to the frequency domain? And essentially it gets stretched in time. I thought it was there somewhere here, but maybe not. Maybe it was when we were doing convolution that's when we saw it. But anyway, I'll just give you the answer, and it's not very hard to imagine also. If a function gets squished in time, like so, it gets elongated in frequency. Okay, so the tile will change from something like this to something like that. And if you make it 4 times the squish, it will be very localized in time, but more spread out in frequency like that. Okay. So a wavelet transform means you take one function, which you call the mother wavelet, and you're taking inner products with just the scaled versions of the same wavelet. You improve the time resolution. So note that if you squish it, its frequency increases. This thing will have twice the frequency as this. Whatever is the frequency here, this will have twice the frequency because you're getting double the number of cycles in the same time. This will have 4 times the frequency. So you're actually going up in the frequency domain. Same time resolution is improving because it's a much smaller span in the time domain as compared to this. So your tiling diagram actually shifts to something like this. And notice now that you are able to capture the transient very well. The transient at higher frequency is now captured very well. So is your, oscillation, had it been at a lower frequency, like an alpha rhythm, it would have been captured very well. Here it's not as great because gamma is a higher frequency rhythm. But you see that the tiling diagram here has changed. Sorry, the time frequency spectrum has changed so that at lower frequencies it's more spread out. So you have got poor frequency resolution at low frequencies. Poor time resolution at low frequencies and good time resolution at higher frequencies. And vice versa in the frequency domain. You've got very good frequency resolution at lower frequencies and poor frequency resolution at higher frequencies. So I have not actually violated my time frequency uncertainty principle in any way, because each tile will still have an area of 1. It's just that I'm using different types of tiles to tile my time frequency space. My tiles at higher frequencies are squished in time and elongated in frequency. So this is good for capturing transients that have power at higher frequencies. And I have got good frequency resolution at lower frequencies, so I can capture low frequency oscillations like alpha or delta or theta and so on. But at the same time, if there's a high frequency oscillation, like notice this thing, this is the line noise at 120 hertz. This is recording done in the US, so line noise at 60 hertz and harmonic at 120 hertz. You can't capture it using wavelet transform. It's just getting washed out. You can capture the transients very well, which you couldn't do here, but you can't capture the high frequency oscillation. But if the oscillation was at a lower frequency, it would have been a nice line somewhere here. So it's a trade-off. Okay, so this is what wavelet transform does. It generates a different tiling diagram here. And if I look at it from a filter bank interpretation, this is the last thing I will talk about today. So remember, if I had a Gaussian window, this is not short time Fourier transform. This is just the windowed Fourier transform. The filters were actually equispaced. We talked about this. This is the Fourier transform of a Gaussian, and it's getting multiplied by the complex exponential, which is then pushing it to a different frequency. So this is when you do the Fourier transform, windowed Fourier transform. When you talk about a wavelet, it's got some shape here. Because it is a zero mean signal, it has zero DC value. So a wavelet actually would look like this. But if you scale it, if you scale this function by a factor of 2 or 4, it actually is just stretching this function like that. So it's a very different way of filtering as compared to this one. Okay, so the center frequency scales, the bandwidth scales with the center frequency. The one that is at a higher center frequency also has a larger bandwidth, something that you are seeing here as well. The one that is at a higher frequency is also more stretched out. Okay, so this is filtering in a different way. In fact, in MATLAB, you could actually just do this. So help wavelet CWT continuous wavelet transform filter bank. construct a default filter bank and display the frequencies. So let me just run this program. And then Frix FB. These are the filter banks corresponding to wavelet transform. See, you are just taking one and you're not translating them as you were doing in Fourier transform. You are stretching them. Each is a stretched version of this such that the center frequency and the bandwidth are correlated. These are called constant Q filters because the ratio of their center frequency and bandwidth is preserved. And this sort of a filter bank, it can be seen in the time frequency domain like this. Okay, so there you go. That's wavelet transform. It's a very deep topic, so I can't really spend more time on that. We will talk about Hilbert transform from the next class. Just read this paper. I think it will, it's a very sort of intuitive and easy way of thinking about these different methods. Okay, and we will move away from filter banks and think about it in a different way when we start Hilbert transform from the next class. Okay, so that's that. I will stop recording now. If there are any questions, please go ahead.